You've probably seen code like this before. You may pause the video if you need more time to read it. Two programs, same values, same result. But in memory, they are already different. Not because of what they compute, but because of how their memory shape evolves over time. By the end of this video, I'm not giving you rules. I hope the next time you write code like this, something in the back of your mind quietly asks, what shape is this creating? I'm K1, welcome to my channel. One quick thing, this video is part of series, so if stack and heap memory or value type reference types are still unclear, I highly recommend to watch the previous video. You can find it here, I guess. Most of us, myself included, learn to think in terms of APIs. LINQ, lists, loops. That's how we are taught. But the runtime is not thinking that way. It doesn't see LINQ, it doesn't see loops, it doesn't see a list of numbers. What it sees is much more literal. Objects, references, and how they are laid out in the memory. The way those objects are arranged and how that arrangement changes over time is what I call memory shape. And once you start noticing that, a lot of things begin to make sense. Let's take a look at the heap for those two snippets. This is usually where something clicks. Both versions already know there will be 1 million items. The difference is not what they build, it is when and how memory gets shaped. In the LINQ version, when we hit dot to list, the code doesn't get all the values at once. Instead, it pulls them one by one through the pipeline. Each value is produced, transformed, and added to the list in sequence. So memory is shaped as the code runs. It is like building the path as you walk on it. Along the way, temporary helper objects appear, iterators, enumerators, and so on. You don't need to know how they work. What matters here is the shape they leave behind. In the loop version, memory is shaped up front, the list is allocated first, and then the code runs inside that space. It is like laying the entire path down and then walking across it. Fewer temporary pieces, a more predictable shape. Same intent, same result, and same usage. But very different memory shape over time, and very different path for how memory evolves while the program runs. At some point, most of us realize something uncomfortable. The performance issues we chase, the memory problems we debug, they rarely come from one bad decision. They come from code that made sense every step of the way. Memory doesn't break all at once. It grows, it shifts, and eventually it settles into a shape. That's what we are really talking about. In this example, at first glance, it looks simple. We created a customer, we created an order, and we linked them together. But what we actually allocated is not just two objects. We allocated a graph. It helps to picture the heap as dots connected by arrows. Each object is a dot. Each reference is an arrow. Here, the order points to the customer, and the customer points back to the order through the list. As long as an arrow points to a dot, that dot stays alive. And because these two objects point to each other, if either one is reachable, both of them remain alive. That's not a problem, and that's not a memory leak. It's just how managed memory works. But this is where memory shape quietly starts to matter, because now memory is not just about how many objects you have, it is about how they are connected and how long those connections stick around. When objects are allocated separately, they don't always end up next to each other. Over time, the heap develops gaps, scattered free spaces, memory that exists, but not in the right shape. You can have free memory overall and still fail to allocate something large and contiguous. This matters between garbage collections. Compacting can help, but whether it happens depends on object size and where those objects live. So sometimes memory is available, just not in the shape you need. The garbage collector's job is simple. From time to time, it asks what is still reachable. That's it. GC is not expensive because it exists. It becomes expensive because of many objects, many references, and scattered layouts. In other words, GC pressure is often decided long before GC ever runs. It is decided when memory shape is created. Allocating memory in .NET is usually fast. Often it is just the runtime moving a pointer forward. The cost shows up later. What hurts performance is not allocating itself, it is allocating many objects, keeping them alive and spreading them across memory. That pattern has a shape, and by now, you know what we call it. You might ask, why does all of this matter? Here is the point. Small design choices quietly define object graphs, memory lifetimes, GC pressure, scalability limits. I'm not here to give you rules. I'm here because I've written code like this. I've shipped it, and only afterward I realized the performance and memory problems come from decisions that all felt reasonable at the time. I'm trying to help us see what the runtime sees. In the next video, we'll look at how passing objects around can quietly extend lifetimes and turn into very real performance problems. Once you start seeing memory this way, a lot of mysterious slowdowns stop being mysterious. If this video shifted how you think about memory, make sure you've watched the previous one. It's the foundation for everything here. You don't walk away coding differently overnight, but you do start noticing things. And that quiet noticing, that's where better decisions come from. Stay with me, grow with me. See you in the next video.